Hi, welcome to another edition of Calculus 2. Today we are going to continue our conversation about series and talk about alternating series. Let's go ahead, take a look at this basic topic. Okay, alternating series. Here I have written some examples so that you can immediately see what we are talking about. It's a series where the terms alternate in sign. So 1 minus a half plus 1/3 minus a fourth plus 1/5. That's an example of alternating series. You could start with positive or you can start with the negative. If you start with a positive, the general look of it will be like -1 to the power of n plus 1 an, where n starts at 1. So -1 to the power of 2 becomes a positive, and then you are starting with a positive. For example, this series here can be written as a sum of -1 to the power of n plus 1 over n, as n ranges from 1 to infinity. This one, you can write it as -1 to the power of n an, because it's starting with negative. Either way. Here are two other examples. This is perhaps a lot easier than the first one. 1 minus 2 plus 3 minus 4 plus 5, and so on. Let's write the dots. And correct this thing. 1/2 minus 2/3 plus 3/4 minus 4/5, and so on. Now, some of these series converge, some of them diverge. And the test is very simple. If the terms of the series decrease and go to 0, the series is going to converge. If the terms of the series do not decrease, definitely it's not going to converge. In this case, the terms of the series lead to something other than 0, and the series still diverges. So we have these examples where the series converges, and these examples where the series diverges. So let's write the general statement. Let's go with one of them. Perhaps this one is easier to write, or that one is the one that you come across more often. So let's write that one, -1 to the power of n plus 1 an, where an's themselves are positive numbers. The alternating series test says that if the limit of these elements of the term of the series is 0, and that they are decreasing, that is, a1 is more than or equal to a2, and that is more than or equal to a3, and so on. Sometimes they write this thing in the following way: an is larger than an plus 1. So as you go down the elements of the series, they are decreasing and they are going to 0. If these conditions are met, then the alternating series converges. Let's go ahead and try to explain this in the context of one of these cases. Let's take the very first one. That's perhaps the most famous example of these alternating series. You notice that, well, the elements by themselves, they are, of course, they are all positive numbers. And then you alternate the sign of them, so you're adding and subtracting. And in this case, it's very easy to see that the terms are decreasing as you go toward infinity, and they are going to 0. If all these conditions are met, then we have an alternating series that converges. Let's go ahead and understand what's going on. So very first partial sum is just 1. The next is 1 minus 1 half. The next is 1 minus 1 half plus 1 third, and so on. 1 minus 1 half plus 1 third minus 1 fourth. So we are starting at a number, we are decreasing by a certain amount, and then we compensate but not completely, so we go up and then we come down and so on. So you notice that we are going to do a zigzag. We are starting at 1, we are coming down, we go up, coming down, and so on. So we are going to have a behavior that we are going up, then we're coming down, then we go up again, but not by as much as before. And that is the basic recipe in the fact that this kind of a series converges. Let's go ahead and take a look at the picture, and that will hopefully convince us a lot better. So I've written the same terms of the same series here, 1 over n. So if you look at them, 1 over n is taken out of this function. Of course, this is a decreasing function. We are looking at the values of this function at whole numbers. So 1 over 1, that's just 1. 1 over 1 half, that's 1 over half. 1 over 2 is a half. 1 over 3 is a third, a fourth, a fifth, and so on. What are we going to do with these things? We're starting at the very first one, and subtract the second one, then add the third one, and subtract the fourth one, add the fifth one, and so on. To see what it's going to look like after we do that, that's what is going to look like. This is, let me show this one. So we started at 1, we subtract a half from it, so we are at a half. Then we are adding a third, so we are to this point. So our zigzag has started. We coming down to this point, we're going up, we're going down again, we go up and down, and so on. Every time the zigzag that we are going to do is a step smaller than the previous one. What does it do? It creates two series for us. One is this upper series that you see that they're coming down, and the other one is this lower series here where we are going up. Notice that both of these series are converging. This one is converging because it's a decreasing function, a decreasing sequence where you have a lower bound, and this one is an increasing sequence where we have an upper bound. So both of them have a limit. Now why should those two limits be the same? Because the amount of zigzag we are going to do every time is getting smaller. As a result, we are going to approach the same limit either from top or bottom. In this famous case, we are going to show later on that the limit that we are approaching to as we go toward infinity is, and in fact, a famous number. It's just the logarithm of 2. We are going to see that in the chapters coming ahead. So let's go back to the calculations that we had here. Let's go ahead and do some examples of alternating series. So suppose I have the sum of minus 1 to power of n plus 1, say, times 1 over n cubed. What would be your verdict about this? Is this alternating series? Well, yes, because this sign is going to alternate. Can you write the very first few terms of this? Well, in this case, we better start from 1 at 0. We cannot start at 0. At the 1, the very first term we are going to get is 1 over 1. The next term is going to be negative because 2 plus 1 is 3, and this becomes negative. So I'll have 1 over 2 cubed, and then plus 1 over 3 cubed, plus minus 1 over 4 cubed, and so on. So it's an alternating series. We can see from the -1 to power that is alternating. Second question, is this thing gonna converge or is it gonna diverge? We said our criterion is that the terms of the series have to decrease toward 0. Well, here it's easy to see that limit of 1 over n cubed. So we set the sign aside, that doesn't make any change here. The limit is in fact 0. And next condition that we need to check, and that is typically the hardest one, not in this problem, but some of the other problems you're going to see, that the terms are actually decreasing. And that is easy to see. Well, the first term is 1 over 1. Is that bigger than 1 over 2 cubed? Well, obviously it is. How about, is that bigger than 1 over 3 cubed? Yes, when we make a denominator bigger, the fraction becomes smaller. So once we have that, once we have these two conditions, that the limit is 0 and they are decreasing, so condition 1, limit is 0, limit of a term is 0, and the terms, aside from the plus or minus, terms are decreasing. These two tell us that this is going to converge. Sometimes from the previous test we can tell something is not going to converge. For example, these two are rather obvious that they are not going to converge. So suppose I have 1 minus 2 plus 3 minus 4 and so on. How would you write that? Well, that's minus 1 to power of n plus 1 times n. Does this thing converge? Well, it's an alternate series for sure, but the terms are not going to 0. Quite the contrary, actually, they are going to infinity. So this one, by the nth term test, or what the condition that you have here, this is going to be diverging. How about the other one? The other one we had 1/2 minus 2/3 plus 3/4 and so on. What would be the formula for something like this? So I have n plus 1 in the denominator. I'm starting at 1 and I am starting with a positive, so I might start with this thing with n plus 1 and go on. Would that one converge? Well, again, this one violates the condition that the nth term has to go to 0. We are not even relieved from any consideration with respect to is it decreasing or not. We don't even need to bother with that. The terms of this, the limit of n over n plus 1 as n goes to infinity, what is that? Obviously it's not 0, the limit is 1, so that one already tells us that this alternating series is going to diverge. How about an example other than these? Let's go ahead and take a look at some other cases. For example, we are going to take a look at let's look at the following, say does sum of say minus 1 to power of n plus 1 times n over e to the power of n, does this thing converge or diverge? So question 1, does it converge or diverge? What do you think? Maybe I wait a minute and then you go ahead. So we said our clue for this thing is that you focus on that picture and try to focus your mind and come up with the answer yourself. Do you think it is converging or diverging? So, well, this problem is a little bit harder than before. First of all, is it alternating? Well, obviously, because of this, it's alternating. Next, is the nth term going to 0? Well, numerator increases, denominator increases, and if you remember from calculus, in the battle of these two giants, this going to infinity and this going to infinity, exponential wins over polynomial. So if you define a function f of x, it's x over e to the x, and then if we ask what is the limit of f of x as x goes to infinity, well, you can use L'Hopital rule. Notice that this goes to infinity, this goes to infinity, so it's a good case for L'Hopital. So you can say this is going to be the limit of derivative of the numerator over derivative of the denominator as that one goes, x goes to infinity, and that's the limit of 1 over e to the x as x goes to infinity, and that's equal to 0. So condition 1, that our nth term should go to 0, that one is checked. So here's does nth term go to 0. So question, we take this, convert it to a continuous function, go back to calculus 1, apply L'Hopital's rule, and then we see that, well, yes, it is going to 0. As a result, we can easily say the limit of the nth term, n over e to the n, as n goes to infinity, this thing is 0. Well, is that it? If the terms go to 0, does that mean the series converge? Well, the main catch in this problem is to establish that the terms of series are actually decreasing. In fact, all that we need is to show it is decreasing from some point on. All the tests that we have for the series, we can just expect that the tail of the series behave the way we are specifying. What the first few terms do, it's not so significant. So next question is, do the terms decrease? Okay, so again, that's typically the hardest part of this problem. Do the terms decrease? Well, in this case, we have an easy check. We can go ahead and take a look at this thing and ask us if this function is decreasing. Well, in calculus 1, we had an easy criterion for that. If the derivative of the function is negative, then we are all done, because that negative derivative means that the function is decreasing. Once again, let me remind you that all we need is to show that that property holds from some point on. Like if after x equal to 5 it was decreasing, is okay, or if after x equal to 10 it was decreasing. That's all we need, is that after some point the function becomes decreasing. So how do we establish that? The way to establish that is to show that the derivative of this function is negative. Is it? So let's go ahead, take this function. It was x over e to the x. Easy way to differentiate it is perhaps to prepare it for easy differentiation. I write it as x exponential of minus x. The derivative of this, so I should apply the product rule. Derivative of first times second, and derivative of the second times first. So let's factor so that we can clean this up a bit. So I can write the derivative like this. Well, what is it that we are investigating? Is the derivative negative or not? Well, denominator always positive quantity. Numerator, if x is 0, well, that's positive. If x is 1, that's 0. If x is 2, this is negative, x3 is negative, x4 negative. So this thing obviously is negative for x is larger than 1. We obviously see that f prime of x is a negative quantity for x's that are larger than 1. What does that mean? It means the function that we are going to investigate, it's going to start to decrease after 1. So we have the following condition also met, that n over exponential of n is decreasing. Okay, when both of these conditions are met, then we can make the final conclusion that sum of 1 minus 1 to power of n plus 1 times n over exponential of n is what? Is it convergent or divergent? What did it say? It is, of course, what we have shown is that it is a convergent series. Okay. Now, it's quite uncommon for us to actually find out what does it converge to. We had a rather rare case, the very first one here. We know this one converges to logarithm of 2. We are going to show that later on. But for this one, well, we are going to have a hard time figuring out anything about it. For some of these other series, sometimes either the problem actually stays open, or it could be quite involved for us to figure out what the sum is. So typically we have to approximate it and such. So let's go ahead and learn a little bit about that. How would you try to approximate what the sum is? Let's go look at something that is perhaps easy on the eye. So let's take a look at the following. 1 minus, say, 1 over 2 cubed plus 1 over 3 cubed minus 1 over 4 cubed, and so on. The question I ask is, well, if you want to approximate this, you have to keep adding these terms. The question comes up, where do you stop? The more terms you add, the more accurate you're going to be. But then how do you decide that enough is enough, and then you can start part B of whatever you are investigating? So suppose we want to approximate this. We need to have a sense of knowing when our approximation is good enough. Well, the way we specify that is to give an error. That is, we say whenever you are sure that your distance to the final destination is less than such and such, then stop. So you say to an error of less than, let's specify some number like 1 in 1,000. We want to have an error of 1,000. That is our aim. Okay, so here suppose we start 1 minus 2 cubed plus 1 over 3 cubed, and so on we go. And suppose we decide to stop. Now we don't know if at the very last we have added or subtracted, so it could be either of them depending on at the even numbers we are subtracting and the odd ones we are adding. So depending on where you stop, it's going to be some number cubed. Well, what comes after that is going to, well, the signs are flipping, so it's going to be the opposite of this one. The next one is 1 over n plus 1 cubed. If you decide to stop after these many terms, after n terms, then the error that you're going to make is going to be less than this, because that's the amount by which you're going to be doing the next zigzag. You're going up by that amount, you're going down by that amount. And as we showed in this picture, let's go back to this picture. When you're going up and down, every time your distance to the final destination is going to be less than the next zigzag that you're going to do. So the next jump is going to tell you, well, the maximum error that you're going to have. So what we say here is that if you want to find out how many terms to add so that your error to the final destination is less than the next, is less than a certain number, all you need to do is to pick the next term and make that to be less than this quantity, and then that's going to tell you what n is, and that is going to tell you when to stop. So here what I do, I write the next term, 1 over n plus 1 cubed. Say if this one is less than the tolerance you tell me, then by adding these terms, I'm making error less than this quantity. Well, how do I solve this inequality? That's going to be another obstacle you need to overcome. You always have the next term less than a thousandth, and then, well, if we cross multiply, this one is going to look like n plus 1 cubed is larger than 1 over 1,000th. Well, 1 over 1,000th is 1,000. Well, let's take a cube root from both sides. So I'll have n plus 1. I take cube root, and then here my cube root is 10. So n has to be larger than 9. So that tells me if I go as far as 10th term, then for sure my error is going to be less than this quantity. So if I go 1 minus 1/2 cubed plus, the last, if I write n equal to 10, is going to be negative 1 over 10 cubed. If I calculate this, the error of this, that is, this value taken as the value of the series, the error is going to be less than 1,000th. So that is the style of problems that you're going to see some of your homeworks. The question is, how many terms should we have for something to happen? Now, sometimes we come across some series that are not alternating, but they do have plus and minuses in them. Well, what do you mean by that? Suppose we take a look at something like the following. Sum of, say, cosine of n over n cubed, and say n is going from 1 to infinity. Is this alternating? Well, you say, well, where's the plus and minus of it? Well, that is not there, but we do have cosine of n, and cosine sometimes is positive, sometimes is negative. It's rather hard to tell, but it's going up and down. It can go as high as +1, as low as -1, and the pattern is not going to be all that regular. It's rather hard to say. Like if you pick cosine of 1,000 or something, you have to think about it a little bit. Is it going to be positive or negative? So when you write this thing out, pluses and minuses show up, but not in a style that we see here. Here is very easy, predictable style, plus and minuses. This one isn't. So this is not alternating. So it's something more complicated because the plus and minuses have a complex pattern to them. The question could face us anyway. Is this a convergent series or is it divergent series? Well, we have a very nice theorem here, and we are going to make a statement about it and practice it, and perhaps in another lecture we talk about it at more depth. One thing we can do is to compare this thing against absolute value of the same thing. If I take this series and put the whole thing in absolute value, I only need to take absolute value of the numerator. This one, well, I'm forcing every term to be positive. Now, we can look at this and ask ourselves, does this thing converge or not? We remember that cosine is always less than 1. So cosine of n over n cubed is always less than 1 over n cubed. And we remember from the p-test or integral test that 1 over n cubed is convergent. Okay, so we forced it to be positive. The positive terms, we can perhaps compare it against something else that we know, and this one we know is convergent. Then we can conclude that the original series, the one that had the plus and minuses in it in a complex pattern, that one will converge as well. So if you know that the series made out of this with only positive entries, meaning, let me restate it, if you force all the terms to be positive and the resulting series is convergent, then the original one is convergent. So we state it like this: if sum of absolute value of elements of a series is convergent, then the sum of that series by itself is convergent. Okay, so we are going to postpone the proof of this thing to another lecture. So right now we're just going to practice. The other possibility is that the series is convergent, but the sum of the absolute values is divergent. So let's go ahead and show an example of that. It's possible, let's write down, it is possible if such a thing happens, that the sum of the absolute values diverge, but the sum of the numbers themselves converge, we call that type of a series conditionally convergent. Then we say sum of an is conditionally convergent. What does this mean? On the condition that you're adding some and subtracting some, then the series converges. But if you force all of them to be positive, then it does not converge. What's a famous example of this? The famous example is that very first item we started with 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 and so on. This one is convergent by the alternating series test. So this one is convergent. But if you force all the terms to be positive, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, by the p-series test or the integral test or a variety of other ideas, this one is divergent. So when it happens that the series with some positive, some negative is convergent, when we force everybody to be positive, it becomes divergent. This kind of a series is going to be called conditionally convergent. That is, it's you have to keep the flip-flop of the signs in place to have a hope of convergence. If it so happens that both of them are convergent, then the one with the pluses and minuses in it is going to be called absolutely convergent. So for example, if I have 1 minus 2 squared plus 1 over 3 squared minus 1 over 4 squared and 1/5 squared and so on, this one obviously satisfies our alternating series test. This is convergent. And at the same time, if you force everybody to be positive, if you consider the following: 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared and so on, this one is also convergent. Then this phenomena is termed with absolutely convergent series. So that the one that when you turn everybody into positive, it is still converging. The original one is called absolutely convergent. Now, one of the most fascinating theorems in calculus is a rather weird property of the series that are conditionally convergent. Conditionally convergent series have a very subtle behavior to themselves. If you take this series and reorder the way the elements are added to each other or subtracted from each other, it's possible that the sum will be different. Now that's going to contradict something that you have learned from elementary school, and it's almost like a fundamental belief item that if you have certain numbers and you add and subtract them, however you add and subtract them, it does not make any difference. For example, if you have 2 plus 3 minus say 4, the sum of this of course is 1, and that does not matter how you perform this task. If you take 3 minus 4 plus 2, that's still 1. If you start with minus 4 plus 3 plus 2, that's still 1. That's still 1. If you have a few numbers and you add and subtract them in any number of possibilities, the result is always the same. We end up thinking that that's always the case. Well, as I said, one of the most fascinating ideas or theorems in elementary calculus is that if a series is conditionally convergent, then the terms of it can be rearranged so that the sum will be any number you wish. I leave that for you to read in the textbook and postpone the description to another lecture. So let's stop here and we meet again. Until then, good luck and God bless.